Eric Parish is a member of the technical staff at Sandia National Laboratories. He received his PhD from the University of Michigan in 2018 and was the von Neumann postdoctoral fellow at Sandia from 2018 to 2020. At Sandia, he works broadly in the field of turbulence modeling, model reduction, scientific machine learning. His present work is primarily targeted at developing and improved modeling capability for hypersonic turbulent flows. We are very pleased to have you here. Please begin the talk.
All right, wonderful. Well, thank you for organizing all this. So today I'll talk about some work I did a few years back on subgrid-scale modeling with memory using the Mori-Zwanzig formalism and the variational multiscale method. And so just kind of as a precursor, there's not really fractional calculus in the work that we're talking about here. We kind of get non-locality in time through this idea of Mori-Zwanzig. So that's kind of the connection to some of the themes that we're talking about here. So before I get going, I just want to, certainly highlight some contributions from Karthik Durasamy, who's a professor at University of Michigan, and then Ayub Gwasmi, who they both, kind of contributed to some of the technical work and certainly some of the ideas behind what I'll talk on today. All right, so motivation. Why am I giving this talk? Who cares? Is that I think as we all appreciate, numerical simulation is a very powerful tool in science and engineering. We're using it for next generation of designs. Something that I work on a lot right now is we're using it in hypersonic flight, uncovering new physics, and we're using it just to understand fundamental physics, what's going on in complex systems. So despite amazing progress over the past several decades, there are certainly a lot of challenges in numerical simulation, and the big one that I'll focus on today is the numerical simulation of multiscale systems. All right, and so multiscale systems are, of course, very commonly encountered across science and engineering. They're in climate, MD, combustion, and turbulence is a very classic multiscale system. And in these multiscale systems, effectively, the main kind of what characterizes them is this, wide range of length and spatiotemporal scales over which important physical processes are acting, right? So you might have very important processes that act at, a macroscopic level, all the way down to, a very microscopic level. And so these multi-scale systems are notoriously difficult to simulate. And the main challenge, of course, is that because of this wide range of length and time scales, when you numerically discretize them, they're inherently very, very, very high dimensional. And so since you need to, discretize all this important physics in space and time, it makes it so direct computations become very prohibitively expensive. They can take, months or even more on modern supercomputers. And so, to actually have a reasonable engineering kind of modeling framework, we often rely on I'll broadly refer to these as reduced complexity methods, where the main idea is that, we try to characterize the system with fewer degrees of freedom. So oftentimes we're only going to model, say, the larger scales, and then we're going to develop some model for, the subgrid scale or unresolved physics. And that's how, really is going to be our workhorse analyses tools. And so, of course, developing these models is very difficult. There's, decades of research on this. A lot of people on this talk have worked on these similar ideas. And so, there's a lot of work that goes into really developing these models. And, that's kind of the pacing item, I would say, in a lot of these simulations. And so what I'll talk about today is, it's applicable to a lot of type of multi-scale systems, but turbulence is going to be really what I will focus on. It's kind of a very representative multi-scale problem, and that'll be, what I'll talk to throughout the talk today. All right, so when you talk about multi-scale, simulation and turbulence, and what do we do for handling these problems? So again, turbulence, you have this wide range of length and time scales. There's also, a lack of scale separation. So things currently cascade from the large scales to the fine scales. And so, you need to either model everything, or you need to either resolve everything or develop good models. And so when you talk about simulating turbulent flows, there's, of course, like the Reynolds average Navier-Stokes techniques where you solve the time averaged equations. And then there's the next fidelity, which is really large eddy simulation. And that's kind of where I'll sit in the talk today. And so LES is, a quite popular technique. It's gaining a lot of attention as we, have more and more CPU power. And so the main idea with LES is that you're going to resolve some of the larger coherence scales and model the very fine scales. So, let's say you have turbulence in a box like I have here. So you're going to resolve, maybe some of the scales that you can see in this kind of contour. But if you zoom in, we're going to be basically developing models for the very fine scales and how do they impact the large scales. All right. And so what I want to emphasize again is the development of these models is quite difficult. This is usually a pacing item. And typically how we do this, we derive them from physical theory. So, things like Smagorinsky, gradient diffusion. That's really, still there's certainly a lot of progress in other areas. But, if you look at, for example, what we do in the national labs, we still rely on, something like a Smagorinsky model. Um, and so if you look at outstanding issues, it's well known that these subgrid scale models that exist have a lot of model form error. So of course they're largely empirical. We know that they're developed and tuned for canonical flows. And so they're known to be inaccurate in important flow regimes. So something I work on a lot right now is hypersonics. So you have hypersonic, shock boundary layer interactions require, very stringent grid resolutions. And so, you want to develop LES models for these types of problems. If you use something like a Smagorinsky model, which we know is developed for turbulence in a box, there's a lot of questions about how it's going to perform in a more complex environment. And so trying to address this is really a pressing need. And I'll also add this, when you get to LES, there's a very fine interplay between numerics and models. And there's like an implicit versus explicit LES debate. And this is, I think kind of an outstanding problem that is still going on right now. And so needless to say, kind of advancing the state of art in LES is a pressing need. There's a ton of work going on in this area. And specifically what I'll talk to in this talk is an approach that we're working on to develop to kind of advance LES by unifying ideas from the Mori-Zwanzig formalism with the variational multiscale method. And that's going to give us kind of a non-local type modeling framework that we can use to derive LES models. And so I'll speak briefly to what each of these Mori-Zwanzig and VMS are. I'll dive into more details throughout the talk, but just kind of starting with a high-level overview. So MZ, or Mori-Zwanzig, is really a type of model reduction framework. So, the baseline kind of formalism was developed by Mori and Zwanzig in the 60s in the context of irreversible statistical mechanics. But then really the starting point for what I'll talk on today is a reformulation in the early 2000s by Alexander Chorin, where they basically took Mori-Zwanzig and they, kind of developed it as this general model reduction framework for a nonlinear dynamical system. And the main kind of takeaway of MZ, and I'll talk to this, is that MZ kind of provides the systematic procedure for taking subgrid scale effects and recasting them as memory effects, which only depend on your resolved variables. And that really is kind of the core idea of MZ. And so if you look in the literature, people have certainly looked at using ideas from MZ to develop, things like LES models. And so in particular, a lot of work has done this for things like Fourier-Galerkin spectral methods. And the results are really quite promising and they're pretty interesting. But it's not always clear how to extend this to more versatile numerics like finite elements. And I would say, more importantly, there's minimal connections with existing methods. And so that's really what I'll talk a lot about today is kind of working through this formalism and unpacking a little bit of what comes out of it and saying, how does this compare to what people are currently doing and draw some of these commonalities. So on the other hand, the variational multiscale method is going to be an LES style approach. It's kind of similar to filtered type LES. The idea is we decompose a state into a resolved coarse scale and an unresolved fine scale state, and then we go ahead and make some mathematical approximations to the fine scales to develop a model for the coarse scales. This would be like our large scale resolved velocities. And so, just like LES, VMS methods require, a subgrid scale model. A lot of times they're derived from mathematical arguments, but you can also do things like eddy viscosity. And so what we're going to do in the talk today is I'm going to basically use VMS as this kind of framework, this vehicle to derive in some sense, my LES equations. And then I'm going to bring in Mori-Zwanzig to develop subgrid scale models for LES. So that's really the kind of way to look at this. We'll use VMS as kind of this framework, and then MZ is going to come in to develop subgrid scale models. All right, so just to kind of outline what to expect over the next 30 minutes or so. I'll start out by kind of developing this multi-scale modeling framework that's going to bring together ideas from MZ and VMS. And then I'll show you this initially, how this works within the context of Fourier-Galerkin spectral methods. So these are defined by being continuously differentiable, which has impacts on the coarse gradient process. And then I'll briefly kind of at the end talk about how you extend this to finite elements and some interesting discoveries that we've made when you take this whole mechanism and you throw it within the discontinuous Galerkin framework for discretization. All right, so yeah, I'll start out by just kind of outlining this idea, this MZ-VMS framework. Like I kind of said, this is going to be a modeling framework going to combine MZ with VMS, and the result of this is going to be kind of a framework that's going to be applicable to nonlinear dynamical systems, and you can actually then extend this to do straightforward application for building subgrid scale models of spectral methods, finite element methods. You can also use this for things like reduced order models. So maybe you're doing like a POD Galerkin method. And so the procedure that we're going to walk through, and I'll kind of just start by highlighting the general steps, and then I'll go through each one of them in detail, is we're going to start with a nonlinear partial differential equation. I'm going to outline a general Galerkin method discretization of this using, say, for example, Fourier basis functions. I'll walk through how we're going to go ahead and do a scale splitting of that set of equations using the variational multiscale method. And then I'm going to bring in Mori-Zwanzig to formally replace the fine scales with the memory term. And that's going to give us kind of a final set of equations that we'll use as a starting point to develop models. All right, so jumping into this. We'll start with this nonlinear initial value problem, partial u partial t plus r of u equals f for some x and omega. So this will be a partial differential equation. For me, this is usually going to be the compressible Navier-Stokes equations, but if you work on different equation sets, this can be a pretty general thing. And so what we'll do is we'll look at kind of a basis type representation for the states. So we'll say u of space and time is going to be some sum from j equals 1 to n of basis functions wj of x times coefficients aj of t. And so of course, anytime you do this, then the state u is going to be restricted to live within this space v. And so this is a standard approach. And then how you would then go ahead and take this and generate a discrete system to solve. For example, the Galerkin method is a very common way to do this. You basically test the governing equations with each trial function w, and that gives you this weighted residual form where you have the inner product between the basis function and the time derivative of u, plus kind of this weak form of your kind of residual operator. And so depending on your system, you might integrate this by parts. But the main idea here is you've taken this nonlinear PDE, we have this basis representation, you have a Galerkin method, and this corresponds to an n-dimensional nonlinear dynamical system that you then want to solve. And so, of course, the challenge for a multiscale system is that to actually do this and get a good answer, right? So let's say you have turbulence, n is often prohibitively large, right? So it's going to be on the order of billions, if not more, for a lot of the applications that we care about. So then, of course, the goal is how do you reduce n to m in an efficient manner where m is going to be much less than n. And so what we're going to do is we'll do this with, we'll start with the variational multiscale method for kind of outlining how we're going to do this. And so VMS is a projection-based, kind of multi-scale splitting framework. It was developed by Tom Hughes in the late 90s. And the main idea is it essentially relies on projectors that are going to project your state into a coarse scale state and a fine scale state. So what you effectively do in VMS is the starting point is a sum decomposition of your solution space or your trial space. So we're going to take V, and so recall on the previous slide I said U is the state, it's going to live within this space V. And so what we're going to do is we're going to express V as a sum decomposition of a coarse scale space. This is V and V tilde in blue. With a fine scale space, this is going to be V hat in red. And I'll use this coloring throughout the talk. So anything you see in blue with a tilde will be a coarse or resolved state, and anything in red will be a fine scale state. And so if you think about, let's say you have like a Fourier Galerkin type representation, the resolved space might be, up to any wave number k. And then resolved space will be, the really fine scale wave numbers for very high k will be the unresolved space. All right, so you have this decomposition of your kind of space V. And so then you can, of course, express your state in terms of, a component that lives in the resolved space and then a component that lives in the unresolved space. So u of x comma t is a sum from j equals 1 to m of resolved basis functions times resolved modes, plus, kind of the remaining m plus 1 to n unresolved basis functions and unresolved modes. So you kind of have this multi-scale decomposition of your state. And so now I'm just going to compactly write that as u equals a u tilde plus a u hat, u tilde resolved, u hat unresolved. And then by virtue of the splitting, you can then basically write two different subproblems for your governing equations. One is going to be an m-dimensional equation for the coarse scales for the u tildes in blue. And the other one is going to be an n minus m-dimensional equation for the fine scales. And so the goal then, of course, is going to be to solve this coarse scale equation. And so in terms of, just classical LES, you can think about this as, the filtered Navier-Stokes equations. And then on the right-hand side, you're going to see that you have basically an unclosed term. You're going to have both the resolved scales and the unresolved scales. So this is effectively your subgrid scale stresses, right? And so if we actually want to solve the coarse scale equation, we have to deal with the closure problem because, you can't just solve this as a function of the blue, the U tildes, because you have, the dependence on the fine scales. So what we need to do is develop a model for the unresolved physics for the subgrid stresses in the context of LES. And so we need to develop this model M, which is only going to be a function of U tilde, which is going to then handle the unresolved physics here on the right-hand side. And then, of course, once you do that, you're going to end up with a closed equation that you can solve. And so, the challenge is how do you construct this model M in a robust and in a systematic way, right? So classically, this is done with, phenomenological arguments, gradient diffusion. You get like a Smagorinsky model. And so we want to do it a little bit differently here. And so for this, we're going to use this idea of the Mori-Zwanzig formalism to go ahead and develop these models. Okay, so what is MZ? So whenever I talk about MZ, I like to always start with a very basic example that it's not MZ, but it highlights, kind of the conceptual idea of what Mori-Zwanzig is doing, and it really unpacks, 80% of the idea behind Mori-Zwanzig in this very simple example. So let's just say you have a basic linear system with two components, a dx dt equals a11x plus a12y, and then a dy dt equals a21x plus a22y. And then just for preciseness, we're going to say the initial condition of this y is going to be 0. And so what we want to do is we're going to look at performing, quote unquote, large eddy simulation where y is an unresolved variable. So think of y as our subgrid scales. So what we want to do is develop a model for the dynamics of x, but it can only be a function of x. So you want to develop a dx dt equals a11x plus some model m of x. Well, for this very simple example, you can actually do this exactly. So what you can actually do is just go all the way back to your first ever class in ordinary differential equations. You can take this dy dt equation, you can treat x as an arbitrary source, and you can just solve this analytically using integrating factors, or it's basically just superposition. And then with that, you're going to end up with an x equation that is only a function of x, right? So I basically solve y as a function of x, I plug it back in here, and then I get this equation here. So I get a dx dt equals a11x plus this integral from 0 to t of this a12 times an exponential of a22 t minus s, a21 x of s ds. And so this really is almost one of the critical take-home points of this idea of MZ, is this process of going from a two-dimensional system to a one-dimensional system results in memory effects. So to exactly represent the dynamics of x, as only a function of x, I need to keep track of its past history in time. All right, and so it's kind of a powerful idea when it comes to modeling that, if you actually want to do this well, you need to have essentially non-Markovian, non-local in time models. And so, this is, of course, a very simple linear system. And, the Mori-Zwanzig formalism, and certainly as it's reformulated by Chorin, really generalizes this idea to nonlinear dynamical systems. And so that's what I'll kind of walk through a little bit here. I'm not going to go through all of the math of MZ because it's too much for a presentation, but I'm going to highlight the important kind of concepts of what MZ is doing. So the primary challenge that we have is if you take, I showed this linear example on the previous slide, and I used integrating factors to remove the dependence on the fine scales. You can't do that for a nonlinear system. Just the math doesn't exist to do that. And so what Mori-Zwanzig does is this really, really clever idea of taking a nonlinear ordinary differential equation and recasting it as a linear partial differential equation that lives within the space of initial conditions, or you can think about it as phase space. So you take this nonlinear ODE and you write it as the Louvel equation, partial v partial t minus L of v equals 0. So here v is going to be any observable of my state. So it could be an individual degree of freedom, it could be a QOI. And then L is going to be this Louvel operator. And so, this is kind of what the form of the Louvel operator looks like. And so, you're not going to be able to, it's hard to dissect exactly what this is doing. So I'll just kind of tell you, if you look at what this operator L is, you basically see that it's a multidimensional advection operator. And so, you can think about it as this is an advection equation in a n-dimensional space where the wave speeds are defined by kind of the right-hand side of your original dynamical system. And so this transformation is actually really, conceptually very simple. We're basically taking a nonlinear ODE, and you're going to look at it in phase space, and it's just like a flow map type description, which is really just described, by multi-dimensional linear advection with, varying wave speeds. So, the catch, of course, this PDE is going to be a high dimensional, n-dimensional partial differential equation. So, you go from this nonlinear ODE to a linear PDE. The expenses, you get this really high dimensional linear partial differential equation. But the amazing thing that you can do with this is, since it's linear, you can kind of play those tricks I played on the previous slide, where you can use this idea of superposition to do things like remove the fine scales from this linear partial differential equation. And so that's really, the genius idea behind this idea. So before I kind of move forward, I'll just make a quick note on some notation I'll use, which will be kind of important. So to denote a solution to this partial differential equation, I'm going to use what I'll refer to as an evolution operator. So I'll say this partial differential equation V at location A naught with time t. The solution is given by this operator e to the TL. So L is going to be the operator for this PDE times V at location A naught at the initial condition. So each time you see this exponential to the TL operator, it's denoting the solution to a PDE with initial conditions of whatever's to the right of it. So these are big boys to kind of evaluate. All right, so that's kind of the starting point of MZ. And so how it then proceeds to do scale separation is you basically define projection operators that operate in the space of initial conditions or operate in phase space. And these projection operators are going to be responsible for eliminating the dependence on your fine scales. So actually the step of the projection operators is where a lot of different work on MZ diverges. So there's two projection operators. There's what's known as Mori's projection operator, and then there's what's known as Zwanzig's projection operator. Zwanzig's projection operator is kind of known as a quote unquote nonlinear projection operator. And that's what I'll focus on here. And so the projection operator that I define is basically going to take some function f, which is going to depend on the resolved scales and the unresolved scales. And then it's going to just project out the dependence on the resolved scale. It's just going to set it to be equal to 0. And so you can almost think about this as a conditional expectation projection, where with like a direct delta density around 0 for the fine scales. Then Q is going to be the orthogonal complement of this projector. And so with these projectors, you can then churn through kind of this Mori-Zwanzig formalism. And you can go ahead and do this manipulation where you take that coarse-scale equation that we had on the previous slide. You cast it as a linear partial differential equation. You split the dynamics using these projection operators, and then you use superposition. And then you bring it back to the ODE space. And this is basically what you end up getting. So the left-hand side is going to be essentially what would look like kind of a normal discretization of the coarse-scale equation. And then the right-hand side is your subgrid-scale model, but we've now cast it all in terms of this memory integral. And so the important thing to note is this memory integral is only a function of the coarse-scale. So at no point in time do you see anything that is red in this. So kind of in the classic sense, this is really a nice result, because this equation is closed in the classic sense. So if you could exactly solve this, you're going to have the precise answer for what your coarse-scale variables are. So in some sense, it's an exact subgrid-scale model. So of course, there's a catch to this, of course. And to kind of outline that catch, we need to jump into a little bit of what this memory term looks like. So I'm going to kind of dive through this, term by term. So what this looks like is it's this. The memory term is going to be a convolution integral of this e to the t minus SL, so that's an evolution operator, times this projection operator, times the Louvel operator. And then this operator is the next one that's going to be really kind of the nasty part of the memory. It's this evolution operator with the dynamics defined by QL, which Q, recall, is the orthogonal projector, or the complement projector of P. And then it acts on this QL A naught. And so the main point is that this memory integral, not only do you have to integrate all the way backwards in time, but you have to evaluate this e to the SQL operator, which corresponds to a solution to what's known as the orthogonal dynamics partial differential equation. And so this is basically, this PDE is given by partial f partial t plus QLF equals 0. And it turns out that this is a really, really, really nasty PDE to deal with. And so, if you're kind of watching along, you might be saying, okay, so we have these n-dimensional partial differential equations. How do you deal with this in practice? Well, this e to the TL operator, because on the previous slide I mentioned there's this equivalence between e to the TL and this partial differential equation, you can kind of jump back and forth between the two and play special tricks. So for example, you can show that this is a composition operator, and that lets you make a lot of mathematical kind of simplifications, which lets you kind of evaluate things easily. But this e to the TQL or e to the SQL, orthogonal dynamics partial differential equation, there's no tricks that you can play. If you actually want to evaluate this thing, you have to directly solve this high dimensional partial differential equation, where again n is the number of degrees of freedom of your discrete system. And so this is of course impossible to do. So the important takeaway is that we've taken this LES, or we've taken this kind of multi-scale system, we've developed a closed coarse-scale equation. And then in that closed coarse-scale equation, that memory term contains all of the subgrid scales, all the subgrid scale interactions, but that memory term is intractable to evaluate. But the idea is that the memory term is instead going to give us kind of a starting point for developing kind of subgrid scale enclosure models. So instead of working from physical theory, we're going to work from this memory term and say, how can we develop principled approximations that are computable to this term and use that as our methodology for deriving subgrid scale models. So that's kind of the goal here. All right, so how are we going to approximate this, right? So you can throw a bunch of math at approximating this. But to kind of get started, I think it's really valuable to take a little bit of time to try to unpack a little bit of how the mechanics of this kind of convolution memory term work, and use that to derive insight into how we're going to model the memory. And so what I'm going to do is I'm going to do a little bit of unpacking the structure of how this memory term operates, right? Like, let's say you had all of the computing power possible. How would you actually compute this thing? Or how would you evaluate this convolution integral? And so to do this, I'm going to look at the integrand of what's inside the memory term. And I'm just going to write this compactly as k of a tilde of t comma s, right? So that's going to be, the integrand. I'm just writing it compactly there. And so trying to understand a convolution integral is kind of difficult. And so what you can actually do is you can take this convolution integral and you can view it as a path integral. So instead of convolving in 2 dimensions in t and s, I can write this as a path integral, which is going to integrate in just 1 dimension tau. And then you're going to have this t and s are going to be parameterized in terms of tau. So this kind of makes it, instead of a multi-dimensional type thing to keep track of, we can just look at integrating in kind of tau. And so how this would work if you actually wanted to evaluate this, I kind of have depicted on a few figures coming on in the next few slides. So here I'm kind of showing you a diagram in TS space of the integrand of kind of this memory term. So this blue line is going to be this memory kernel K evaluated at a tilde of t, and then I'm going to set s equals to 0. So you can think about this blue line as, let's say you're doing a computation. At any point in time, this blue line you can just compute using your current state, right? So this is just, some function of a tilde of t. But then if you want to evaluate this memory term, for each point in time t, you then need to solve this orthogonal dynamics equation, which is going to use the initial conditions from here, and you're going to solve this out in pseudo time s. And so for each t, you evaluate your simulation, you would then need to solve this orthogonal dynamics equation. And then at the end of the day, the kind of memory term that you want is going to be a path integral backwards along these lines. And so to kind of better depict this, I have like a couple animations, and this is really going to drive the main model I'll talk about. So let's kind of look at this kind of similar plot. So what I'm going to do, I'm start by outlining kind of a line moving through space. So this is going to be this, starting this blue line that I referred to on the previous slide. So this is just the memory kernel evaluated at a tilde of t comma s equals 0. And so then to evaluate that whole memory integral, I'm going to move out into kind of this s dimension, this pseudo time. And then basically for every pseudo time, you're solving this orthogonal dynamics equation. And so it's going to kind of create an integrand that might look something like this, right? So this is like your integrand in TS space. And then at the end of the day, what you care about is this integral backwards along this line. So that's kind of what the memory effects look like. And so just to kind of reemphasize, this blue line, everything computable in a normal simulation. In order to actually then get kind of the surface, you would need to solve the orthogonal dynamics. But right, that is at least kind of the mechanics of how this term is going to operate. And that, at least for me, has given me a lot of kind of visualizations and understanding of what's going on and how to develop models of this. And so from that, we can actually look at a very, very, very simple way to model the memory term. And so the simple closure that I'll kind of talk to mainly in this talk is the tau model. And what we're going to do is we're going to leverage the idea of finite memory effects. And so we're going to assume that the memory decays in finite time, tau. And then with that memory, we're just going to basically come up with a very simple quadrature rule for approximating what's going on in this integral. So let's say, we could just do something like do a trapezoidal quadrature rule where we're just going to take this value here. We're going to multiply it by, technically 0.5 times some length scale tau, and that's going to give us an approximation to what this memory integrand is. And so that's, kind of one of the most simple ways that you can use this whole philosophy to develop a subgrid scale model. And so there's a lot more, sophisticated models that you can develop from this. You can develop non-local in time models. You can develop, additional transport equations. But they're all kind of based on similar ideas to this. So, I'll kind of refer you to the end of some of the papers that we've worked on to show you some more complicated model forms. But for the setting of this talk, I'll just kind of focus on this idea. So we're going to have this kind of model that's derived from a basic quadrature rule. And so what the form of this looks like is this whole memory integral is approximated by some constant tau, and this will be the memory length. So it's going to be a parameter we have to specify. And then it's going to be multiplied times the evolution operator, e to the TL, and then you have this P, L, Q, L, A tilde naught. So, certainly not very interpretable what's going on here, and I'll talk to that in a little bit. But this is a mathematical simplification of what this model ends up being. And I guess what I'll highlight is all of this is easily computable within a numerical simulation. So you don't need to evolve any extra transport equations. It's just essentially a function of your current state. So then what I'll mention is, right, we now have a parameter tau. We have worked on some procedures to find tau. So what I'll mainly show you on, what I'll mainly present on today is a model where we use a dynamic approach to compute tau. So effectively, we copy and paste what you do with dynamic Smagorinsky, where we use assume scale similarity, and we use the Germano identity to dynamically compute tau at every time step in a simulation. I'll also mention you can do things like approximate this from theory. You could play tricks like do error bounds and try to minimize your error bounds based on inverse estimates. So you can do things like that also to approximate tau as well. So we have this tau model, and now I want to talk a little bit about what it actually is doing, right? So I kind of outlined that, I'll go back and a few slides. I kind of outlined that this tau model is given by this almost ridiculous looking term here with P's and L's and Q's and L's. And so I want to spend a little bit of time unpacking what this actually is. And you gain a lot of very interesting insight from doing this. So the kind of going at this term, right? So we're going to try to evaluate this e to the TL, PL, QL, A tilde naught. And if you take each of these operators and you are patient and you work through a lot of your mathematics and you kind of just do your bookkeeping right, what you can do is you can show that evaluation of these operators yields this term here. And I'll unpack this a little bit. So this is given by basically an integral in y and x of your residual, the right-hand side, r of u minus f. That is then going to be projected. This pi hat is going to be the projection onto your fine scale space multiplied by the Jacobian of your residual function. And so essentially what this is showing you is that the memory term is driven by, effectively you take what you can resolve, you take the right-hand side, you project it onto your space, you look at the complement of that, and then you multiply it by this inverse Jacobian. So it's a residual-based term. So that's kind of a very powerful thing, is that this MZ tau model is basically driven by the coarse scale residual. And so this is really kind of exciting when we discovered this, because it opens up a whole bunch of commonalities between what we're doing with MC and what's been done classically. And so for those of you who aren't familiar, in the classic finite element literature, there's a whole range of stabilization techniques known as residual-based stabilization. So if you look at something like like Subgrid or so like streamline upward to Petrov-Galerkin, there's also Galerkin least squares, there's adjoint stabilization. So all these methods are residual-based stabilization techniques. And so what we were able to show is that there's a lot of similarities between these techniques and MZ. And so in particular, it's very close to adjoint stabilization. And so it kind of gives us a very common language to explain, how are these models performing? Why are they doing what they're doing? And gives us kind of a new avenue to analyze. And I think looking back at some of this work, I think it's pretty cool that you can look at a very classic technique like Subgrid, and you can tie this back to non-locality in time. You can tie it back to MZ. You can tie it back to memory effects, and all these things are connected in some sense, which I think is very, very interesting. All right, so just to kind of recap where we are. So I outlined this kind of MZ VMS framework. I'm using VMS to decompose that PDE state. I bring in MZ to replace the fine scales with the memory term. And then I unpacked a little bit of some of these models and showed how they're very common, similar to residual-based stabilization. And I outlined a very simple model to the memory term. And so now I'll just briefly show a little bit of slides about how do these models do? What do they do well, and what do they not do well? And so I'll start out by just looking at a canonical example. It will get more complicated than this, I promise, but we'll start out with a very canonical example of the viscous Burgers equation. And so we're going to look at, this is the problem setup we'll look at. It's just going to basically be, you're going to have like a sine wave that moves into a stationary shock, and then it's going to decay. We're going to discretize this thing with just a Fourier-Galerkin discretization. So we'll just look at, sines and cosines as our basis functions. And then here on the bottom right, this is kind of what the energy spectra looks like. So you can see, as the solution kicks off, energy comes out to high wave numbers, and then it gets dissipated. So this is going to be, it's kind of a very basic under resolution example. And so to actually resolve, all this with Fourier-Galerkin methods, you need 1024 Fourier modes to resolve this thing. And so I'll look at doing, quote unquote, LES of this type of system. I'll use only 16 Fourier modes. And that's going to be, 1.5% of what we needed for that, direct computation. And I'll show results for, the full dynamic, quote unquote DNS. I'll show a no model result. I'll show results with this dynamic tau model that we developed, and then I'll compare it to the Smagorinsky model. So here on the left, I'm showing you the energy spectrum evolving through time. So black is going to be the truth. Green is going to be the no models calculation. Blue is the MZ model, and then red is going to be Smagorinsky. And so what you see is that, of course, if you don't include a model, you have all this energy bouncing around at high wave numbers. You can't dissipate things. And then when you go to the MZ model in blue, you almost perfectly track kind of what the energy spectrum looks like as you move through time. And then the solution in red is the Smagorinsky model, and you see that you might do a decent job in terms of dissipating total energy, but you don't do a very good job on where should that energy be in wave number space. And then on the right is what I'm showing you is just total energy integrated in time. So, black is truth, blue is MZ, red is Smagorinsky, and green is the no model case. And you basically see the similar story here. The no model case can't dissipate energy. Smagorinsky does an okay job, and then we do really quite well here with MZ. So this is one of the first results we had gotten when we did this work. And then we've pushed this to much more complicated examples. And so the next thing I'll show is let's say you do this for homogeneous turbulence. I'm going to look at the same type of thing with a Fourier discretization. Here, RE lambda is going to be 164. So it's not a crazy high RE lambda, but it's reasonably high. So for DNS, you need 1024 cubed modes, which of course is a lot. And then I'm going to look at doing LES where we have 128 cubed modes. And I'm going to show kind of on the bottom left, I'm just going to go ahead and show you the energy spectra. And so here, black is, again, the truth. Green is going to be the no model case. Blue is the MZ. Red is the dynamic Smagorinsky model. And so what you see here is that, if you have the no model case where you don't include any models for the subgrid scales, you get this, very poor behavior where you have a buildup of energy at high wave numbers. And then when you go to the dynamic tau model, you do a really nice job of doing, accurately kind of capturing the energy spectrum. And you are, doing at least as well as dynamic Smagorinsky, if not a little bit better. And then another pretty interesting thing is here on the right, I have the transfer spectra, right? So how is energy being moved by the subgrid scale model to, from one wave number to the next? And same kind of color scheme, black, blue, red. And so what is interesting about the MZ model in blue here is you actually do see there is a little bit of backscatter from the MZ model. So they are capable of depositing energy into some of the higher wave numbers if you want. And you compare that to, say, dynamic Smagorinsky. Dynamic Smagorinsky is just purely dissipative across all wave numbers. And so for this example, we find that this MZ process does a lot better than dynamic Smagorinsky in terms of how is energy being transferred. So the solutions, we're probably getting the right answer for more so of the right reason. And so now I'm going to kind of move to highlighting kind of a deficiency of MZ. So I'm going to take that exact same example, and I'm going to go ahead and look at just a coarser discretization of this exact same problem where I'm going to run, the DNS is going to need 1024 cube modes, and LES is only going to need, I'm only going to use 64 cube modes. So in the previous slide, I was using 128 cubed, and now I use 64 cubed. And so now the story is a little bit different that you see. And so here, again, same color scheme. You can see how bad, the no model is. So you definitely need subgrid scale models. Now MZ in blue is doing okay. You're definitely, vastly improved over the no model case, but you do see a little bit of buildup in the high energy wave numbers. And then if you compare that to dynamic Smagorinsky, you see, dynamic Smagorinsky is doing a lot better, especially at the higher wave numbers. And if you look at the transfer spectra, you see dynamic Smagorinsky is looking a lot more, analogous to what you see in the DNS than what the dynamic tau model is giving you. And so it's kind of interesting. If you could, let's just look at the DNS curve between these two plots. You see, DNS has completely changed because of how we have a different coarse graining process. And so I think that this result kind of speaks to these MZ models I talked about. We had this very simple model going all the way back to this figure. We had this very simple model where I'm taking the state, I'm multiplying it by a memory length, and that's how I'm getting my subgrid scale effects. As we become more and more and more unresolved, right? This memory length is probably going to get longer. It's going to become more complicated, and this model form is basically going to break down a little bit. And that's exactly what you see in this example here, right? As we get more and more coarse, MZ does less well. And it's also interesting how some of the physics specific models start doing a little bit better, right? So it's not always a clear story. I think there's a lot of V and V you need to do on a model to convincingly show better results than something like a classic method. So yeah, so that being said, I'll show one more example. And this kind of just highlights one of the really nice things about MZ. Right, so if you think about where we're increasingly going with numerical simulation, we're doing multi-physics, you have numerous governing equations, and developing subgrid scale models for these just becomes harder and harder and harder because, right, you have to have understanding of, different types of physics, how they interact with each other. And the nice thing about this kind of MZ process is it just systematically gives you models from the governing equations, right? It doesn't give you don't need phenomenological arguments. You just get it out of the governing equations. And so the last thing I'll look at for this is going to be the ideal MHD equations. We're just going to do turbulence in a box. I'll again look at Fourier-Galerkin spectral method, and we'll look at forced homogeneous turbulence. And so here, I'm not really even going to show you comparisons to an existing model because as you get to multi-physics, it's not even clear what the right existing model is. So dynamic Smagorinsky doesn't is totally garbage if I apply it to this problem because you also have the kind of the closure problem on the MHD side. And so here's the energy spectrum on the left. And then this is the energy spectrum for the fluid, and this is the energy spectrum with respect to kind of like the magnetic energy. And you see for both types of physics, the MZ model does quite well. So again, black is DNS, blue is MZ, and green is going to be the no model case. and you get systematic improvements. Even for this, kind of complex multi-physics application, which, I had run this with zero knowledge of MHD. And so I think it just kind of it shows a little bit of the power of what you get out of these types of models. All right, so just to kind of like briefly outline where we are thus far, I showed, Berger's equation, homogeneous turbulence, and MHD. I also want to say I've looked at Taylor-Green vortices and channel flows. And in general, these MZVMS models, they're accurate and they're robust. They seem to work for a wide range of problems. They sometimes outperform problem-specific physics models, but if you really get to this regime where they're very severely under-resolved, they don't work quite as well as maybe something like a very physics-specific model. And so now I have a couple of slides left. I think I'll move through these, kind of quickly, just in the interest of time, since we got started a little late, and it's a Friday afternoon, so everyone's probably trying to get out of here. So what I'll briefly highlight. So everything I've showed so far is the application of MZ to spectral methods. And so the differentiating aspect of spectral methods is they're continuously differentiable. So when you work through kind of that MZ VMS process to get your governing equations, that plays a role. So if you work through something like a finite element method, like CG or DG, it's a little bit different. And so for DG, what we'll look at doing real quick is applying this whole framework to DG. So in DG, the main idea is you're going to use local polynomials to represent the solution. So you're going to take your domain, discretize it into elements, and then on each element, you're going to represent U by polynomials. Local polynomials. So you can do linear, you can do high order elements on each polynomial. And so in our framework, we're going to basically do this, and then we're going to apply scale separation on each element. So we're going to say, let's say we have kind of our discretization, and then we're going to go ahead on each element. We're going to say, resolve up to some polynomial order m-1, and then the kind of the fine scales will be higher order polynomials, and that's how we'll formulate things. So in the interest of time, I'll move through quickly, but the main kind of takeaway is that when you have these DG, or same thing with finite element methods, just CG, the kind of the weak form, you end up with element boundary operators that you have to keep track of. So this can arise, for example, from integration by parts. And in the context of DG, these show up in the forms of flux functions. So you have like an upwind flux or a central flux. And so you need to go ahead and account for that in all of your mathematics. So if you work through the MZ framework, you kind of get the same kind of process where you're going to have this coarse-scale equation. It's going to have your flux functions. You're going to have this memory term. But now if you go ahead and unpack the memory term, you end up with a bunch of different operators. So you have 4 types of operators that show up if you unpack what is going on in that, say, tau model. And then the main thing I'll highlight is that these terms basically include permutations of the strong residual operator as well as the flux operator. So you actually have residual contributions and you have flux contributions to your memory term. And so in particular, the flux contributions are quite interesting. And so what you can do, I'll kind of jump through. What you can do is you can go to linear advection. You can just look at a straight linear advection equation, partial u, partial t plus partial u, partial x equals 0. I can go ahead and write out the memory term. And if I'm very patient, I can work through deriving all of this. I can start with the DG method with a central flux. And what happens is that this memory term actually ends up in only modifying your flux function. And it actually ends up giving you an upwind flux. And so, for those of you who are not familiar with DG, upwind fluxes are basically the way that we get numerical stability in DG methods. And so from this idea of Mori-Zwanzig, from this idea of memory, you can basically just derive an upwind flux, all from this idea of closure, which, is that actually, useful in practice? Not really, but it's kind of highlighting these kind of thematic similarities between existing ideas, Mori-Zwanzig and memory effects. So, academically, it's a very interesting kind of process to see this link between MZ and upwinding. And then the last thing that I'll kind of talk to a little bit is if you go ahead and take this and you apply this to a nonlinear problem like Berger's equation, you're going to find that these subgrid-scale models are going to contain both flux schemes as well as volume closure terms. And so, if you look at usually how we do stabilization for discontinuous Galerkin methods, all the attention really goes on the flux side. There's not really that much attention that's given to the volume side. So what I'm going to do is I'm going to show you just kind of some MZ models applied to Berger's equation. We're going to again look at that standing shock problem. And I'm going to kind of show you two different regimes of this problem. The first one will be a low order example with 8 elements in second order. And the second example I'll show you is going to be a very high order example where we're just going to have one element and then we're going to have a 16th order element, a 16th order element on the domain. And I'm going to compare, kind of an MZ based approach to something that's used in practice, which will be the standard row scheme, the row flux scheme. So that's what I'll kind of compare to. And so if you start out by looking at, this case where you have 8 elements in second order, so this is, a pretty canonical type of configuration that we would actually run with, that has been run with in practice. Here on the left, I'm going to show you the evolution of total energy in the domain. And then on the right, I'm showing you a physical space solution. So black is going to be the truth model. Green is going to be a baseline DG model that has a kinetic energy conserving flux, so it has no mechanism to dissipate energy. Blue is going to be an MZ model built on top of that, and then red will be kind of a DG with the rho flux. And so if you look at total kinetic energy, both rho and MZ look like they're doing more or less the same. But then if you go to solution profiles, you see MZ does a nice job at correcting this kind of no model case, but it doesn't do nearly as well as say the rho flux or something like that. And so rho better captures the local solution. So I'm certainly not advocating using MZ to build a new flux scheme. But what you then can do is see something a little interesting. If you go to the second case where you have one element in 16th order and you have to develop a stabilization type scheme for this type of problem, you find that what we do today doesn't really work. So again, this is the same idea. Black is DNS, blue is MZ, and red is going to be kind of the baseline row scheme that we would use. And here now the baseline row scheme is woefully inaccurate, and that's because it doesn't account for how should you add dissipation, how should you model the subgrid scales that are appearing kind of in the volumetric sense. And so it's only really adding dissipation at the interfaces, while the MZ model actually really looks quite nice overall. And so it can actually account for how should we add dissipation to the volume terms. And so here on the right is the physical space solutions. So MZ in blue is, it's kind of like oscillations, but if you take the DNS and you project it on the solution space of the polynomials, it really looks like it compares very well. And so this kind of demonstrates the importance of volume stabilization terms, which is really not done at all in DG. So I think this is kind of an interesting area of future work, is to use ideas from VMS and MZ to go ahead and derive new stabilization approaches for something like discontinuous Galerkin, particularly high order methods, which is it's known to be very difficult to have good stabilization schemes for these problems. So I think that's kind of all I have. I guess we're probably a little bit over. Yeah, so I'm just in summary kind of outlined this modeling framework using MZ and VMS. What I want to highlight was we use VMS as this vehicle to get our scale splitting, and then the important thing is that MZ gives us this coarse-scale equation that's non-local in time. I talked about how we can approximate the memory term in MZ, and then I connected this to residual-based methods. In particular, there's a lot of commonalities with MZ models and things like adjoint stabilization, which is well known in the finite element community. And then I showed you a bunch of numerical results where I think we probably covered the takeaways of those results pretty well in the talk itself. Yeah, so I'll just stop in the interest of time and thank you guys thank everyone for their time.
Thanks, Eric, for the nice talk. Regarding the questions, I request the audience to kindly raise your hands and I will call out your name as they appear on my screen. All right, nobody has a question, so I have a question, but probably a trivial one. So, in the case of DG, you had a simple example where a 1D simple example, and then you were talking about how the term appears for the flux. So was it only in this, but you should also have, in addition to the flux term, or is the flux terms, you should also have something for the element itself, right? Yeah, was this the example? Yes.
Yeah, so
Yeah.
if you look at linear advection, which is, since the dynamics are linear, the way that all the math works out is volume contributions all go to zero because of the fact that it's linear. And the only contributions that end up being here are going to be a flux contribution.
So
So it's
this is
just
very
because,
specific to example.
yeah, so it's just because it's a linear equation, it just gives you a flux contribution. So if you go to a nonlinear example like Berger's equation, so yeah, I mean Berger's equation with, I mean, yeah, everyone knows what Berger's equation is. Then since it's nonlinear, you end up with both like a flux term, which you can, actually analyze, you can write it down, and you also end up with a volume term. So what it says is, in order to, build in my Subgrid-scale effects, I need to, add stabilization to the fluxes as well as stabilization to the volumetric part. Yeah.
And in general, you will have like four terms, right? You showed at one of the
Yep.
slides. Okay. So the first one is so that's the volume. The
Yeah,
first
so
term.
this is, yep. So you can think about this is the volume, like the volume Jacobian acting on, the
Yeah,
coarse-scale residual of the volume term, basically. So
I
like whatever
see.
you
So it's
can
omega
evaluate.
x, omega y. I see. And then there is there is omega x and gamma y.
Yeah,
Okay, and
yep,
there is a gamma term. I see.
yep.
I see. I see. So, so in general, if I've understood it correctly, like, and correct me if I'm wrong, first we will discretize the equation and then we'll apply the MZ theory, right? And not the other way around.
Yeah, that's correct, right? Because the MZ theory is basically, the way that
Hmm.
it was formulated that we use, it's derived for dynamical systems. And
Yeah.
so
So
you
you
use that, yeah.
need PDEs. You need a series of PDEs, and discretizing it gives you a series of PDEs.
Yeah, like a series of ODEs. Yeah.
Yeah, a
Yeah.
series of ODEs. Sorry. Yeah.
Yeah. And so then
So,
what
yeah.
we do is, we do the coarse graining in ODE space, basically.
Hmm.
Um,
Hmm.
and you can write everything as like a weak form PDE with finite dimensional spaces if you want to.
Okay, okay. I'll have to sit down and try to learn this math. And if you have some references on that, that would
Yeah.
be nice because this was a nice high level overview. But I'll have to. I would like to do it with my hand as well.
Yeah. Here's some references, and we have a book chapter coming out hopefully in the next few months, kind of highlighting some of this. It's not published. It's not. They're doing final proofing. But I can
So
share that when it's out.
do that. So then I'll distribute across this FC channel so everybody gets it. So whenever you're ready, whenever it is published and it's public.
Yeah.
Because yeah, MZ is a nice way of getting non-local operators.
Mhm.
I probably had one thing else in my mind. Um, okay, in the case of DG, I saw that your results were much better. So I'm purely speculating that's because of your brute force of approximation of your integral over there, right? That what it looks like to me because you had an integral and then you approximated with a tau, not even with a Riemannian sum. You had a very brute force approximation of that integral.
Yeah. Yep. Yeah. So that's where all the improvement is coming
Well,
from, is from like this
yeah.
approximation.
But
Yeah.
then, that should be the same for the case of DG as well, because it's the approximation of the integral is pretty much the same, right? But in DG, your results seem to have improved, and I'm trying to understand what's happening.
Yeah. I mean, it gets complicated fast because everything is derived from the discrete, like the discretized PDE, right? And so different numerics have different properties, right? So like even though the methodology is the same, you take something, you apply it to like DG, let's say that's like dissipative. Let's say you do DG with like upwind fluxes.
Mm,
That will give
mm,
you different models than
mm.
DG with central fluxes, or DG with, or like a Galerkin, a CG Galerkin method. So everything is very
Yeah.
specific to the numerics,
Mm.
which I think it's a good thing and a bad thing. So it's a good thing in the sense of, you give me a code, I can, kind of work through the machinery and give you a model that's very specific to how you discretize and with your code.
Hmm.
But it's also it's a bad thing in terms that, the models are not as universal. They're designed for a specific model, a specific type of numerics.
Yeah, fair enough, because this does not start from the PDA. This first starts from discretized version of the
Hmm.
PDA. So it depends heavily on how do you discretize. If you have a very bad scheme,
Hmm.
then that error keeps accumulating to the point we have garbage. Uh,
Hmm. Hmm.
yeah. So yeah. So I was thinking of like if you have the time. I mean, I'll be curious if you can if you can do an a priori test. Are you acquainted with this? You know, this LES people in the community do this a priori rather than doing the whole
Hmm.
simulation. They just look into the
Hmm.
statistics. So it's not computationally heavy, and probably you could finish it in a week as well. So just approximate that integral in a better way, and then you can publish an a priori paper on this.
Yeah, it's like one of the things that's really hard about doing this is in general, you can't evaluate this. Like it's not, even if you have, months evaluating this integral is basically impossible without making additional simplifications. So in order to, building systematic approximations to it and analyzing them like in an a priori fashion is hard because it's hard to get like the truth data. In some sense, the only thing you can extract is the integral of it, but like actually like extracting what's in the integrand um, is it requires solving this orthogonal dynamics thing, which is very hard. So I can like develop models and then tell you, is the output of the model correct? Does that work? Does that do it? Can I validate that? But then to like tell you, am I modeling the memory in a good way, if that makes sense, that becomes very hard to do.
I mean, right now the question is more on the physics. So as a proof of concept, however difficult it is to compute it, if there is a way,
Yeah,
you
yeah,
can
yeah.
make a small example and do a proof of concept. The physics is right, so you can
Yeah.
okay, physics is established. Then you move on to the next part. Right now, my question is the error coming from the model or the
Mhm.
physics or is it the numerics, you see.
Yeah.
So you
Yep, yeah,
address
yeah.
this kind of questions, but anyway, I see that this has a lot of operators embedded inside the integrals, and I'm not sure if these operators, so if there is a p and l, can this be written as l and p, or it has to be in the same order?
It has to be in the same order.
Okay,
Yeah,
so
some
you have
some
a
operators
difficulty.
commute, but yeah, some
Yeah.
operators commute, but in general they don't commute. Yeah.
But okay, so it will also depend on like what's the PDA. So okay,
Hmm. Hmm.
fine. Fair enough, fair enough. All right. Uh, does anybody else have a question? I guess no. So probably this is a good point to close this talk. Thank you very much, Eric, for giving this nice talk. If you have any final words, go for it. We'll
No, thanks
close the
thanks
session
for
here.
setting all this up. Yeah. Yep.
Always a
Thank
pleasure,
you.
Eric. Always a pleasure. Yeah,
Yep. Thanks. Appreciate it. All right. Have a good one.
yeah, yeah. Bye.